Hello, and welcome to this tutorial in uncertainty in ultrasonic measurement. We'll begin with the definition of measurement uncertainty. Uncertainty expresses the range of values that can be reasonably expected when making a measurement. This is a brief tutorial to what is a complex subject, and the ISO IEC guide to the expression of uncertainty measurement should be consulted for further information. It's also useful to consider the measurement hierarchy. At the very top level is the standard international system of units upon which measurements are based. Below that are national measurement institutions. Their role is to maintain and to disseminate primary standard calibrations, and, through the process of international cross-comparisons, ensure that the results from one NMI are consistent with those from another. At the next level down, we find calibration laboratories. Many of these are certified to IEC 17025. And below that again are industry and university test laboratories. As we go up through the levels, we get closer to the SI units and therefore our traceability increases. But as we descend through the levels, we find that uncertainty increases. It's also useful to consider the NMIs who are currently active in ultrasound. Foremost among those are the National Physical Laboratory in the United Kingdom, PTB in Germany, NIM in China, and NMIJ in Japan. All of these laboratories maintain primary standard calibration facilities in ultrasonic power, ultrasonic pressure, or both. Let's now consider the different types of uncertainty. Uncertainties are classified as either Type A, those which are amenable to statistical analysis, or Type B, those for whom model-based analysis is required. It's the combination of these two classes of uncertainty that leads to our total uncertainty estimate. Let's now look at Type A uncertainties. If we make a number of repeat measurements, we can determine the mean. This is simply the sum of all the measured values divided by the number of measurements there were. Similarly, we can determine a standard deviation. And finally, the uncertainty can be established from the standard deviation divided by the square root of the number of measurements multiplied by some constant. Here, the constant relates to confidence interval. So what do we mean by confidence interval? Consider a Gaussian distribution characterized by a mean value, as shown. If we consider a region within one standard deviation, either side of the mean, we find this encompasses 68.3% of the population. If we extend this to 95.5% of the population, we need to extend the range to 2 standard deviations either side the mean. And finally, at 3 standard deviations either side of the mean, we encompass 99.7% of the population. Therefore, for a confidence level of, say, 95%, the specified range, that is, 2 standard deviations either side of the mean, will contain the true value of the measured data with a probability of 95%. Let's now look at Type B uncertainties. An example of this is when we digitize analog data. Consider the number of digital levels shown, and an analog waveform. Because of the finite number of quantization levels, when we digitize this waveform, we find it can only take certain acceptable values. For values that are in between the discrete data levels, these will be coerced to the data level up or the data level down, and this will introduce an error. And there is no preference for where in that data range values get coerced. In fact, anywhere between one data range and another, there is a rectangular probability distribution function. If we characterize that by half ranges A, then the uncertainty associated with that is as shown. If we now consider temperature variation, and this could be temperature variation of the electronics associated with a preamplifier, or the variation of sensitivity of a hydrophone's active element, these variations more commonly take on a Gaussian or normal probability distribution function, in which case we can determine the type B uncertainty as shown. For many measurements, the most significant cause of type B uncertainty will be the calibration uncertainty of the reference device used in that calibration. Let's now look at the combination of uncertainties. Uncertainties are combined in quadrature. So we take each individual uncertainty, square it, add the squares together, and then take the square root of the resultant. If we're looking at a quantity that involves another quantity squared, in this case, if we look at ultrasonic intensity, which is proportional to pressure squared, and that pressure is expressed in terms of an uncertainty, in this case UP, the uncertainty in the derived parameter, the ultrasonic intensity, is twice the uncertainty of the pressure parameter. For typical values of a pressure uncertainty in a hydrophone calibration of 12%, this leads to an uncertainty in the intensity of 24%. It's also important to consider cascaded uncertainties, and this is particularly important when we look at the dissemination of a standard from an NMI downwards. So at the National Measurement Institute level, the uncertainty for that calibration will have been determined from the combination of type A and type B uncertainties. This will be used to provide a reference hydrophone or power balance that goes out to a calibration laboratory. That calibration laboratory will then undertake its own assessment of uncertainties, which will include its own type A and type B uncertainties, but also the uncertainty level from the NMI. Note that the total uncertainty from the NMI is just one contribution to uncertainty at the calibration laboratory level. If the calibration laboratory is then calibrating a device to go to an industry or university test lab, then when the test lab conducts its measurements, it too will have its own type A and type B uncertainties, combined with all of the uncertainties from the calibration lab. So as we descend each level, the uncertainty budget becomes larger and larger. So in summary then, we find that uncertainties fall into two groups. Type A uncertainties are evaluated statistically. Type B have to be modelled. And uncertainties accumulate quickly. It's therefore important to try and minimise them wherever possible. We hope you found this interesting. If you did, come back and find some more of the Precision Acoustics tutorial videos.